our session, the first in the spring semester. I'm happy to see everybody and hope that our work will be fruitful in this semester. Let's go, Vitalii.
Okay, first of all, thank you so much for the opportunity to give a talk. My talk is devoted to stochastic block model in a new critical regime and the interacting multiplicative coalescence. It is the joint work with Vlada Limic from Strasbourg. We will consider the following random graph, which is called the stochastic block model. Stochastic block model. You can see what I write, right?
Yes.
Oops. It is the graph which contains some number of vertices. Say we have vertices are divided on two classes. We assume that we have two classes of vertices, one class and the second class. Where we have the same number of vertices, say n here and n here. Also, the geometry doesn't play no role. We just assume that vertices are labeled by 1, 2, 3, and so on. Geometry play no role. And also, let's for convenience assume that vertices from one block is numerated by odd numbers, and vertices from another blocks are numerated by even numbers. So here we have the block with vertices 1, 3, 4, 5, and so on, up to 2n minus 1, and here we have 2, 4, 6, and so on, up to 2n. And we draw edges between vertices from one group independently with probability p. So we draw edges, say, with probability p. So the probability, it is the probability that vertices labeled by I and j are connected. Oh, that we have. Okay, we have edge. And also the same here in the second group. Say something like that, also with probability p. The interclass edges, the edges between different groups appears with independently with probability q. So here we have edges which appears with probability q. Okay. Our goal is the investigation of the scaling limit of the graph as the number of vertices goes to infinity and probability that edges appears goes to 0. Goal. It is scaling limit of the graph as n goes to infinity and p that will depend on the number of vertices, and q, which depends on number of vertices, goes to 0. To be more precise, we want to consider sizes of connected components of the stochastic block model. What two vertices belongs to the same connected component if they are connected by some path. On the picture here, one connected component is like probably, let me a little bit modify to have something, interesting, more interesting. So say that is one connected component, and that is I think it is okay. It is that another one, and also the third connected component. Let's denote, let's Cn. Oops, I'm sorry. Let Cn, it's the vector C1, C2, C3, and so on. Where here is the size of the largest connected component. The size of largest connected component. Here is the size of the second largest connected component, and so on and so forth.
Vitaly, let me ask you, as I understand, you don't make any difference between connected components from one block or between the connected components which contains points from different blocks.
All right. We first of all, we add edges with different probabilities. Then we forget that we have two different blocks, and we look at the connected components.
I see.
The question is, we are interested if there exists a limit or of that vector after some scaling as n goes to infinity. So, does exist? Does a limit, a scaling limit? I mean, we want to normalize Cn somehow and then make n to infinity, scaling limit of Sn as n goes to infinity. And before I will formulate the main result, I want to consider first of all some special case. The case when the probability P of appearing of intraclass edges and the probability Q of appearing of interclass edges are the same. Special case. P is equal to Q. In this case, we get the graph which called Erdos-Renyi graph. Erdos graph. By the way, I didn't tell that sometimes we denote that graph like Jn. It means that every group has n vertices. P, it is a probability inside of appearing of edges inside one group, and Q between different groups of vertices. That case, that Erdos-Renyi graph. Here we have in that graph we have two n vertices, and now the probability of appearing of all edges is P. The existence of a scaling limit of the vector of connected components was already presented recently for that graph by my co-author Vlada at this seminar. And I just want to recall that result because it will play a key role in the studying of the stochastic block model. Let's assume that now we have a graph which has not two n vertices like here, but it has only n vertices. Let's consider J and P. where the vertices are labeled by numbers 1, 2, and so on up to n, and the probability that H appear between vertices A and G is equal to P. Then if we take P, which is equal to 1 divided by n plus K divided by n 4 divided by 3, for some fixed number T from R, and we take n so large that that probability is between 0 and 1. Let's also denote the vector, the ordered vector of sizes of connected components by ER, like Erdős-Rényi. It is the C1 of T, C2 of T, and so on. That is the first largest connected component of the Erdős-Rényi graph. That is the second, and so on. Since we have finite number of vertices, starting from some number, we will. I mean, we have only finite number of sizes, but let's fill that vector up to infinity by zeros, and so on. Also, let's normalize that vector by 1 over n divided by 2 divided by 3. Then it is known, that result was proved by Aldous. 97. For every T from R, the vector, the ordered vector of the sizes of connected components goes in distribution to some non-trivial limit in the space of L2 functions. But let me also put here just in the space of in L2 space of all sequences, but which are summable in square. But also let me put here arrow. We will consider only elements from L2, such that xk are decreasing. I'm sorry, it is from L2, such that xk decreases. And that limit can be described as follows, where x star of T is the ordered sequence of lengths of excursions of the Brownian motion with drift. Ws is a standard Brownian motion, plus, and then we have a drift, a parabolic drift. T is, remember that T is a fixed constant, minus Ts square divided by 2, above path minimum. It means that that length of the excursions of the process, let's denote that by S, WTS, of the process WTS minus minimum WT from 0. Again, if we have, just let's consider a picture. If we take that Brownian motion WTS, then draw the graph. Then the excursions above path minima, it is that excursions. Here also you have many excursions, but my picture is not good enough for. I mean, it looks not. I mean that graph doesn't look as the typical trajectory of the Brownian motion. But anyway, so it is something like that. Then if we take that excursion, if we order them, that we get exactly the limit, the weak limit of the rescaled vector of sizes of connected components of Erdos-Renyi graph. That process X star is called a multiplicative coalescent. It's called. Say just xt is called a multiplicative coalescent. Do you have any questions here? Okay, it is the result which if I remember correctly, was already discussed here, and also which I would like to use today for the discussion of the stochastic block model. But now let's just look at that result to understand what we can get immediately for the stochastic block model. Let's come back to stochastic block model. Of course, if we take P is equal to Q, and that is equal to 1 over the number of all vertices, to n, and take T and divide also 2n to the power 4 divided by 3, then in that case the stochastic block model is the Erdos-Renyi graph, and we know what is the limit, the 1 of 2n 2 divided by 3 c1 of t, c2 of t, the limit of rescaled vector of sizes of connected components of that graph, and according to the Aldo theorem, it converges to the multiplicative coalescence. But our goal is a little bit to study the limiting behavior of stochastic block model when one probability is asymptotically different than another probability. We will interesting the case when Qn is asymptotically smaller than Pn. That the probability that edges between vertices from different classes appears with asymptotically smaller probability than the edges inside one group. I think also that that model can have some application, for example, from the point of view of formations of networks, where the connection, say, between people inside one group can appear with higher probability or much higher probability than connections between different groups. We will assume, and it is a formulation. I want to start the formulation of the result which we discussed today. We will assume that Pn behaves like 1 over n plus t divided by n 4 divided by 3, and Qn is equal to s divided by n 4 divided by 3. For here t is a fixed number, and s also is some fixed. And in this case, we will see that there exists a non-trivial limit. There exists limit 1 1 over n 2 divided by 4, the same rescaling. C1. I also will put here, I mean, the sizes of connected components depends on T and S now. I will fix them here. And so on. After some number, we put zeros to have infinite vector. And we will see later that that limit can be described by two multiplicative coalescence with some interaction. The limit will be given, and it is two independent. Maybe it's better to write can be described. Can be described via or using independent multiplicative coalescence with interaction. Before formulate the precise result, I would like to give some intuition here. Let's come back to the picture. We have two groups of vertices, n vertices here and n here. Say, okay, 1, 2, 3, 4. It is too much. We need to have the same number. Also, and we add edges inside one group with probability p, that which now is 1 over n plus t n to the power 4 divided by 3. And we do the same there. Like this. The number of vertices in one group is equal to n. The same here. Therefore, if we don't have any edges between that two groups, what do we get at the limit? Of course, in the limit, and it is trivial, we get two independent multiplicative coalescence. I mean, also we consider the number, the ordered vector of sizes of connected components of that graph, rescale it, and we get that vector goes to multiplicative coalescence at time t, and the same here. Since we added edges independently, that multiplicative coalescence will be independent. And it turns out that interclass edges which we add Qn, which are equal to Sn to the power 4 divided by 3, will provide the interaction between that two multiplicative coalescence. Let me describe the type of interaction and formulate of the main result. Restricted multiplicative merging, or shortly RM. Let's define the following random map. First of all, we fix S. S plays the role exactly. I mean, S, it is the same S which is here. And also, let's take independent identity distributed random variables with exponential distribution with rate 1. I, j are larger or equal than 1, and define the map RMMS from L2 times L2 to L2 decreasing sequences as follows. We take x1, x2, just let's consider the vector, a graph labeled by 1, 2, 3, and so on. And also to every vertex, we prescribe some mass. To the first vertex, to the vertex labeled by 1, we prescribe x1, then x2, and so on and so forth. The same we do for the second sequence. I didn't tell x and y is from L2. Y1, Y2, Y3, Y4, and so on. And then we do the following. We draw an edge between x, between vertices from Z group and between of that group, if the following conditions are satisfied. I mean, we draw the edges here. If psi 3, 2 is less or equal than x3 multiplied by y2 s. Again, the edge between xi and yj is open if that, I mean, for all omega for which that is satisfied, yj. We will have probably here graph. We can have, say, there and there, and after that we consider the connected components. Of the connecting component here. It is like connecting component and so on. And consider the masses of that connected component. Recall that every vertex has a mass, that vertex has mass x1, that has y2, and so on. We consider their we sum all x and y from the corresponding connected component, and build the ordered vector. So RMM S of x, y, is the vector of ordered masses of connected components of corresponding graph. Do you have any questions?
Actually, yes. Why it will be mapped from L2 multiply L2 to L2? Why we know that the result will be in L2?
If you want to do the precise computations, I mean, very careful computing the probability that edges appears, then directly it can be shown when x and y has very small norm in L2. I will tell about that a little bit later.
Okay.
But if you want to prove that for any x and y just by the direct computation, then then it is not easy to do. But here you can use one trick. Let's assume that also you add edges between vertices from the same group. according to the same rule which we did. Then in that case, when we consider the vector of ordered masses of connected components, it is exactly the vector, it is exactly the value of the multiplicative coalescence at time s, at this time s, which start from that configuration, And here then you can say, okay, we know that starting that the multiplicative coalescence which start from the point from L2 also must be an L2 using, for example, the result of all those.
Vitaly, to think as you told us, we have to know that that new age between y and x between y and x accordingly to the previous picture when you have two blocks. But is it true that this is exactly the same probability if we have number, for example, y2 and x3 in blocks, and then every h arise with probability q? Is it true that it is the same probability as you mentioned? You connect x and y, but you have to pay attention to that x and y are the numbers of the points in this connected component, as I think. Yeah. So the h arise between arbitrary points from this component. Moreover, in your previous model, several h can arise between the same components.
Okay, let me be here more precise, because I made probably a very large jump without explanation of details. Let's for a moment forget about the stochastic block model which we considered, because we will come back.
Then my question remains. If we forget about stochastic block model, then my question remains.
No. Of course. And now let's do the following trick here. We want to we add edges. Also, let's take another family, say xi prime. It is independent exponentially distributed random variables and xi2 prime. And also we add edges according to that rule. Y, say y, y2s. Then, and we consider that random graph. And let vector z of s, it is the vector with components which are just the masses of the coordinates of that vector, infinite vector, is masses of connected components of the vector, where that green edges also are present. Then, and now, first of all, let's compare that map and that map. I mean, at least what we can say about that two maps, that that two vectors. If you look at the corresponding graphs, then that graph is a subgraph of that graph. Because that graph, the graph with green edges, it has more edges than the graph where are presented only red edges. And therefore, in that case, when you look at the norm of that vector and you compare it with the norm of the corresponding vector, which corresponds to the graph only where red edges are present, then of course you have that inequality. It just follows from the fact when you add x1 plus x2 square is always larger or equal than x1 square plus x2 square.
Yes.
Therefore, if you can say something about finiteness of the norm of the vector z, then you can say also you know that the norm of that vector is also finite. And now it turns out that when you do that trick which I did, it is the graphical description of the multiplicative coalescent, which start from the point from the vector, say like that vector x1, y1, x2, y2, and so on. That is L2. Oh, unfortunately, here I cannot tell you more because as I said, in order to prove that if you have the multiplicative coalescent which start from L2 and leaves also it is an element of L2, you need to do a lot of analysis to prove that. In fact, the idea is to look at, if I remember correctly, that process, which is a semi-martingale, and using the martingale methods, you can show that this process, this semi-martingale, is always fine. It is
So
at least for me, who is not an expert in random graphs, how that can be overcome just using some facts from random graphs.
So there is a reference for this result, yeah?
Right. And I'm sure that Vlada mentioned that the last time when he very carefully discussed the multiplicative coalescence, and then she told that having the multiplicative coalescence which started from L2, it always remains in L2.
Okay.
So I was referring only to that. But later, as I promised, we will see that that it is always so, at least when x and y are small.
But what happens if s is equal to 0?
You have no edges, and then of course, and then that vector which you get.
It's just the sum of the two.
No, it is like you need to take the vector x1, y1, x2, y2, and so on. Just mix that and order it, because you have no because you have no edges.
But here it's clear that it will be in L2 or not.
Yes, it is in L2.
And if you add some new edges, it will always.
No, you will get something which will have the norm larger than in the case s is equal to 0. And then the question is, okay, cannot it happen that for some s large enough, you will have that it is not element of L2.
Yeah, true. Okay.
Okay, then let's formulate the main result. Let SBM. It is the vector which we it is the vector of consistence of the it is the ordered vector of sizes of connected components of stochastic block model. And I'm sorry. It is C1 T of S. Of course, it depends on N. C2 T of S, and so on. Also, Qn is equal to S n4 divided by 3. Pn is 1 over n plus T n4 over 3. Then theorem. Konarovskyi lineage. The process stochastic block model, I mean that rescaled vector converge in distribution to RMMS of x star of t, y star of t in A2, when x star and y star of t are independent multiplicative coalescents and also independent of RMM. I mean independent of psi, which appears in the definition of RMM.
So do we have convergence for fixed T and S?
Right. When we fix T and S, we have the convergent. And at the moment, we cannot improve that result. If we come back to the result devoted to the Erdős linear graph, then that result can be improved, and one can show that we can build the coupling of stochastic graphs such that you will have the convergence, say, in the Skorokhod space for all t simultaneously. But at the moment, in our case, we can prove that only for fixed t and s, and later probably you will see the reason. Okay, another questions? If not, then I would like to tell you about the idea of the proof of this theorem. And let's assume idea of proof. Let's come back to the stochastic block model and draw a picture, but now I want to draw the following picture. The vertices from one, okay, I mean, we have the vertices of one block. We have n shtuk. And also from the another block. And you see that that vector we rescale by that constant. Let's prescribe to every vertex the mass, which is equal to exactly that number that we use for the rescaling. And so on here. Also here, let's also assume that we have vertices, but here we have masses which are equal to 0.
Up to infinity.
Up to infinity, right. We do the same for the second block. And so on, and the last, the n's. And then we have zeros. Of course, we have the edges between that, which appears with probability Pn, and here also with probability Pn. And here the edges appears with probability Qn, which is equal to s divided by n 4 divided by 3. Let's present that probability as the probability that the random variable, exponentially distributed random variable with rate 1, is less or equal than some constant s multiplied by xi xj yj, where here I use here is xi and here is yj.
So as far as I understood, the edges between points which have 0 mass cannot arise, yeah?
We consider them, we also say that they appear, but now the probability that they appear is equal to 0.
Mhm. And let us recall again, psi ij has which distribution?
Psi ij has exponential distribution with rate 1.
So we can calculate this S precisely because
This Sn
X, Y,
precisely.
and
Right. And
yes,
let's do this. Just we know that S divided by N for let me change the color. S divided by N4 divided by 3 is equal to that probability, but that probability it is 1 minus exponent minus Sn multiplied. We consider only the cases X and Y which are non-zero. Not zero. Then here is 1 and 2 divided by 3 multiplied by 1 and 2 divided by 3. And then in that case, Sn, it is minus n to the power 4 divided by 3, ln 1 minus n s divided by n 4 divided by 3. And you see when n goes to infinity, it goes to s. Okay, so we choose that Sn. We presented we present the edges in orange color according to that event, and then we will get the stochastic block model. But now I want to consider that picture from another point of view. Now let me copy everything what we have. And first of all, we present only edges in red color between the same groups and build connected components. Here, probably here, there, and so on. Oh, and let's the vector xn of t. It is the vector which is the masses of connected components. It is the vector, the ordered vector of connected of masses of connected components. Or if you like, it is 1 and 2 divided by 3. And here we have C1 of t, C2 of t, and so on, where that C, it is the sizes of connected components. In this graph, where the edges appears with the same probability Pn. And we do the same for, let me denote that vector by part x1t, x2t, and so on. And we do the same for xnt for the second graph. And so on.
But these y's are also dependent on n. Is it
they
correct?
also depend on n, thank you.
But converge to some limit, as you told us before.
Yes, it converges exactly to x star. To the standard multiplicative coalescent x y star of t, and that converges to x star of t, according to the result of all. But now, using the property of the exponential distribution, let's say that is for fixed omega. It is say x that is x1. That is say y2. And then we put the edge between them if the random variable psi ij, this is independent of x and y, is less or equal than s multiplied by x1, y2. So with that probability, here is Sn. Let me Qn, that is, no, I'm sorry, no Qn, but just with, if we put the edge, if psi ij, in that case 1, 2, is less or equal as, and then the mass x1 of the first component and the mass of the second component.
Vitaly, so are you going to prove the following? Assume the following continuity. Assume that you have two vectors, say xy and x bar y bar, that are closed in L2, and then you make this procedure with IID exponential, and then if these two vectors are closed, then and you coalesce with your method, then after the coalescence, new vector will be closed also. Yes. So
no,
is this idea or not?
I want to say the same. I want to say the following. If first of all we merge, just consider that connected component, and then we draw the edges according to the same rule. Which we did before, where we check whether xi is less or equal than Sn multiplied by the masses of the corresponding components. Then we get that the distribution of the vector built using that graph, that procedure, and the vector here have the same distribution.
Mm-hmm.
Oh, but what is, I will say about a little bit just in a second. I just want to say, if you just put the edges here according to that rule, then the vector, and then you consider the vector, the ordered vector of the masses of connected components, it is exactly R, M, M, S, N of X and T, comma, Y and T. And I say that it has the same distributed as the vector, that vector which we consider here. SMM, N of, let me, T, comma, S.
Yes. So and now you just want to prove continuity of this,
right? Mm-hmm. I mean, it was the main idea that just using that observation, you can reduce the problem with stochastic block model to the problem of continuity of RMM map. Therefore, the result, the main result which I presented, will follow from the following proposition. Yes. Which says the following: let xn goes to x and yn goes to y in L2. Also Sn goes to S. Then RMM Sn of x and yn goes in probability to RMMS x of y in L2 decreasing.
Vitaly, and you use the same exponential random variables in the left-hand side and in the right-hand side.
Right. We use the same probability space and the same exponential random variables, right? Mm-hmm. Another questions?
And do you have almost sure convergence?
I do not know. We cannot prove the convergence almost surely. We have the convergence. The first step of the proof of that statement is actually, it is trivial when you have the sequence xn of the form like x1, x2, and so on, xm, and then you have zeros. I mean, the Taylor's is uniformly bounded. I mean, after some number, you have all zeros. When you have such a vectors, then in this case, the convergence is almost surely. Because you have a finite number of edges and then
You mean m fixed and m is not changing, only m?
No, I mean, yes, m, it is m fixed and does not depend on N. It is uniformly, like you have uniformly from some number you have all zeros. Then in that case we have that RMMSN of X and Yn converge almost surely to the RMMSXY. Why it is so? Because you have because if you take omega such that for every vertex psi I j is strictly is not equal to t to s, I'm sorry, to s x x I y j from that set for every, I mean intersection over I and j, then for such omega you have exactly the continuity, right? Then and this event has a probability one. I hope here the continuity is clear, or I should say more.
Yes, it is clear because you cannot switch between sizes of components.
Yes, right. I mean, you just freeze the picture. I mean, starting from some. I mean, the picture is frozen starting from somewhere. So therefore, the main problem of the continuity here is somehow to control the tails. I mean, what we do for the continuity, we just split vector on two parts, and we use the continuity for that type of continuity, and also we work somehow with the estimate of the tails, and there we can work only with probabilities, and therefore, unfortunately, our method doesn't allow to show convergence almost surely. Since I have 3 minutes, so if you allow me, I just can say just a couple of words. I mean, which probably gives you a rough idea in the proof of that proposition. At least what we do there.
You mean about the estimation of the tails?
I mean how we split that only, because and also one word about the estimation of tails. Maybe it makes sense to say only about the estimation of tails. Okay, then let me just.
Okay, because it seems that tails for the size of components for the graph you mentioned must be specific, not any L2 vector. Yeah.
All right. Here we use two facts, at least, which I learned working on with LADA. The first one, if we work with vectors in with ordered vectors in L2 space, which are connected somehow with random graphs, then we have a good estimate for norm when we consider two random graphs and the corresponding vectors related to that random graphs. I will say about that in a second. Just let's say that we have a J bar. It is a graph with vector to with vertex ways xi bar. And also J, it is a subgraph of J. Subgraph, it means that each edge of that graph is also edge of that graph. And also let's assume and with ways with vertex so xi, I mean for that graph. Also, let's assume a bar. It is
Vitaly, if you wrote something, for example, I cannot see.
Yes, I see. Let me start sharing again. I see that the translation was stopped. Just a second. Georgi, could you give me? I will leave the meeting by my tablet and will connect again. Please give me allowance to do that. Georgi, are you here?
I'm here, but you are not connecting.
Okay, I see. Okay, then let me do the following. I just will share the screen on my computer and will use the board there. Just a second. Oh, okay. You can see now another board, right? No, what is that? Then you have one graph. You have, as we said, one graph J, and then you write A. It is the ordered vector of masses of connected components, and also for J, and also A bar. It is the same, but for J bar. Then it turns out that the norm A bar minus A square is less or equal than the norm A square minus the norm A to the power square.
Maybe a norm of A without bar.
Here is A bar minus A, the norm of A bar square.
Oh, I see. Okay, yeah. In the order. Okay.
Okay, you just can consider that as an exercise. I mean, it is not complicated to prove. Therefore, if you want to consider, then now let's consider the vector ZT, which is obtained. It is the ordered vector of connected components of the graph which we consider. I mean, it is x1, x2, x3, and so on. xm plus 1, and so on. I mean, we put edges there, consider the methods of connected components, and so on. And also, let's consider I will use such a notation. What we do there for that, we just truncate that graph, let's say, and put here math 0. And do also the same procedure with the same psi. Of course, that graph, which corresponds to that vector, is a subgraph for that. Then you can estimate. You can control the norm of z of t minus the norm of z m of t larger than epsilon, say epsilon, less or equal than the probability the norm of z of t square minus the norm z of t square. And for that probability, we can prove that it is less or equal than 1 divided by epsilon, And here we have the expectation of that let me write like that, strictly larger than m, the norm square, multiplied by the expectation of that, and here I put m. I'm sorry, here should be polynomial. Polynomial, which depends on t, the norm of that less or equal than m of t square. And that is polynomial of order, of degree 2, of degree 2. Therefore, what you need to do, you need to just uniformly control that expectation, show that it goes to 0, and show that that expectation is bounded.
Mhm.
But here we can use exactly, we can work with, in order to show that, by the way, I didn't say what that vector is, but that vector is like, you just consider that part, you add edges, and then you build that vector here. I mean, that vector and that vector, they are independent. They are taken from different groups of vertices. Good, and just using using the we can estimate the probability that two vertices are connected. We can control that one, and that it gives us the good control of the corresponding expectation. It is a very rough idea of the proof.
Mhm. Okay.
I think it is everything what I can tell you, because I have no more time anymore. So thank you so much for your attention.
Thank you very much for interesting talk. And now maybe somebody have questions or comments, please. If no, I have a question, Vitaly. When I said about tail behavior of these vectors, I thought that it may be more special, and I expected actually not such say general technique like you showed us, but I expected that you will say, okay, if we have a special graph, then its graph of components decrease with the same speed which we can control. Do you know something about these things, or only about the limit distribution?
I cannot unfortunately answer that question.
Because you see, if you have even weak convergence and can control the speed of this convergence in some relatively to some distance, you know the behavior of the excursions of this process, and maybe it can be interesting to see the speed of decreasing of this components, sizes of components.
You mean now we consider that vector, we just truncate it by just consider m vertices,
yes,
right?
surely, yeah,
and then we are interested when m goes to infinity.
Yes, how fast?
Yeah,
exactly, yes.
But I think that it should be okay. It is an interesting question, an interesting problem, but for me it should be more complicated, that say something about the difference, where we just want to compare them up to epsilon and want to estimate the probability. So I mean if you want to use some known results, what you want to make that by hands.
I mean
but I cannot say so much about that. I mean
that the statement of Aldous about the weak convergence maybe can be specified. You can say something about the rate of the convergence, something like this one, in order to control the behavior of this vector under the large n. Yeah.
Mhm.
Also, as you mentioned, you don't have the complete result when you have a process like for one block model. Yes.
Mhm.
And what is the difficulty?
The difficulty
You cannot build the picture. Yeah.
The difficulty is, first of all, the difficulty is, I think, unfortunately, I don't have more slides, but in the previous slides, first of all, the identity, I mean, when we don't have the continuity of an map, say almost surely at least. We have the continuity only in the probability, and for me, it doesn't allow to say anything about the behavior of the process. And the second, yes, and probably it is the main difficulty. I mean that we don't know enough properties for of that map, which allows to take the stochastic block model and map that, or consider that as just some map applied to the Erdős-Rényi graph, for which we have the convergence as a process.
I see. Okay, then thank you again. And for today we finish our work. And I don't remember who is the speaker next week. Maybe Georgi, no?
Ivan Fещенко.
Okay. So we will continue functional analysis stuff, Vitalii. So next week. But for today, thanks everybody and bye.